Now it started, sir, again.
Okay, so what we have to remember is like this way. If this is our quadratic form, okay, ax square plus by square plus cz square plus 2fyz and 2gzx and 2hxy. So what we will do, we will write the coefficient a11 will be the coefficient of x square, a22 will be the coefficient of y square, and a33 will be the coefficient of z square. Okay, and a12 will be the half of this should be xy actually, because if you're taking x, y, and z, this is x, y, and z. So we will take this way. X times x square. So coefficient of x square. X times y. So xy. So we'll take the xy. So half of this coefficient. Okay. So similarly, x times z. So half of the coefficient of zx. Okay. And y times x. The coefficient will be half of the coefficient of xy. Okay. Similarly, y times y, that is y square, coefficient of y square. Y times z, coefficient of yz, half of that. So basically, we are making it symmetric. Okay. So as an example, if we check, so 1, 4, and 6 is there. Okay, third diagonal a11, a1, a22, and a33. After that, this is x1, x2, and x3. So similarly, x1, x2, and x3. So x1 into x2, okay, half of this, so it will be 1. 1 is actually half of 2. So it is 1. Okay, half of this. x1, x3. x1, x3 is 3. So it will be half of the 3. So 3 by 2. Similarly, this is nothing but half of this coefficient. Okay. Similarly, other entries are calculated accordingly. Okay. So that is how we will get one symmetric matrix. Now, in the last class, we have seen if A is symmetric, a real symmetric. We are talking about real symmetric. Real symmetric matrix. Real symmetric matrix. Then we can find then the eigenvectors. Eigenvectors of A are pairwise orthogonal. Okay, we have seen that in the last class. Okay. So the question may be in the reverse way also. Okay, write down the quadratic form for the corresponding matrix A. So let us check whether it is symmetric or not. Okay, 1, 2, 5. So 1, 2, 5. 0, 3, 0, 3.
Go to the previous slide.
Yes, tell.
Okay, sir. Thank you.
Okay. So the quadratic form is actually we have seen the Q can be written as X transpose AX, or if we write it, okay, to keep the syntax similar, where X is X1, X2, and X3 is any vector, any non-zero vector. Okay, any non-zero vector X. Then if we can find this relation, then if we multiply this, okay, this matrix and with this matrix, then we will get this expression, a row matrix. After this row, and this is a column matrix, row matrix and column matrix, if we multiply, then we are getting this. So what we need to do is actually take the coefficient of x1 and x2 together. Okay. It may be in the reverse order, x21, x23, x12 and x21. So we can take the collect. So this is the required QA. U1, U of x1, x2, and x3. Okay. From a given quadratic form, we can find the coefficient matrix. And from the coefficient matrix, we can find the quadratic form.
So can you go to the previous slide, sir?
Of course.
Before this, sir. Sir, you said the symmetric matrix that we are going to find is C, no, sir? In definition, you wrote like
Yeah,
half of A plus A transpose is symmetric matrix C.
yeah.
So, sir, in the next slide, so that A represented like it is actually C, sir. In the next slide,
Yes, yes. This one.
this matrix is C, sir.
Yes, this is C actually.
Okay, sir.
Actually, this matrix is C.
Sir, here x1, x2 is 1, yeah.
X1 and X2.
Yeah,
Tell me.
in the matrix.
Which one?
And even x2, x1 is 1, yeah.
X2, X1.
Yeah.
See, the coefficient is actually X1 and X2.
Yeah.
Okay, the coefficient of X1 into X2. So whether you write it X2 into X1, that does not matter.
Okay, sir.
In which order you are writing. Just a minute.
Sir, in example also it is C, no, sir?
Yeah, it is directly C. So just a minute. Yeah, X2, X3. So the 1 is there. So we'll divide by 2. Okay. So the coefficient of this one, sir, this one. Okay. Okay, then we'll move forward. Okay, so how to find? I think we have discussed it. I don't need to explain everything again. Just to write that we have also seen that we can make the eigenvector for a symmetric matrix. If A is a symmetric matrix, A is symmetric, then the eigenvectors of x1, x2, and x3, okay, will be orthogonal or pairwise orthogonal. Now what we do, from here we will define alpha 1, okay, by dividing the length. From here we will define alpha 2, x2, and from here we will define alpha 3. Okay, Now, if we take and further, we will define P as this matrices. Okay, we'll take this column vectors in the alpha 3. Then P will be orthogonal matrix. Okay, if we take for orthogonal matrix, we have seen P equals to P transpose is equals to P inverse. Okay, so if we multiply this P inverse AP, then we will get a diagonal matrix that we have seen already. The diagonal matrix. Okay. For symmetric matrix, this this transformation is actually called congruent transformation. That is orthogonal transformation or congruent transformation. And finally, if you take this matrix, okay, suppose this is the coefficient matrix, coefficient matrix of a quadratic form. Suppose this is a quadratic form, then we know from the quadratic form we can write the from the coefficient matrix we can find the quadratic form. So if we write here our x, we'll take one matrix x, y, and z. Okay, then x transpose will be our x, y, and z. So if we multiply this matrix, so x transpose dx, so what will happen? We'll write x, y, z. We'll multiply. Okay, let me write down. Okay. So if we write here, let us take here. So x is our, sorry, we'll write vector as capital X, y, z, and x transpose is x, y, z. It is a row vector or row. Then we have seen D is actually lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. So if you take x transpose D x transpose dx, then we'll have x, y, z multiplied with lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. And the column vector is x, y, and z. So from here, we will get that lambda 1 x square plus lambda 2 y square plus lambda 3 z square. Okay, so the matrix is actually from the given, okay, from a quadratic form x, y, z, we will get a matrix. We'll get a symmetric matrix. Okay, so here actually mixed terms are there also. Ax square plus by square plus c z square. Then plus 2 f xy plus 2g. Suppose this is xz plus 2h yz. Okay, then the matrix will be A, B, C. Half of xy, that is F, half of xz, D.
Sir, here also actually it is C, no, sir?
Yes, this is C matrix. I am writing. So don't bother about the name. Okay. Let us write C actually. Okay. Normally, you just have to, okay, without name, what will be the matrix, the coefficient matrix? F G. Okay, that this is F B, and this is H G H T. Okay. So from here, from this matrix, this is a symmetric matrix. We will get this P matrix, P and P inverse. Okay, we'll get P and P inverse. From these two matrices, we'll get that P inverse AP is equals to D. Okay, so if we get D here, and if the D is a coefficient matrix of a particular quadratic form, then what will happen? Then the expression will become this way. So the mixed terms actually 0xy plus 0xz plus 0yz. 0yz. So what we are doing actually, we are transforming this quadratic form. Okay, this is QF quadratic form, and this will be known as, okay, this, from here we are reducing it. We are actually reducing it. So this is actually called canonical form. Canonical form. Okay, so the mixed integer will not be there. Mixed entries, x, y, and xz. Only we will have x, y, and z. There is no term x, y. Mixed terms are not there. Okay, so this transformation is called congruent transformation. Okay, or orthogonal transformation.
Sir, is there any relation between these two quadratics?
Relation. This is the relation. It was actual quadratic form. Okay, we are reducing it to its canonical form. Okay, sometimes it will be called sum of squares. Okay, this canonical form, sometimes it is called sum of squares. Only square terms are there. Okay, the question may be, write the canonical form. Okay, reduce the canonical form. Reduce the canonical form. Sorry, the quadratic form. Write the quadratic form into